Well, hello, everyone. Welcome back. So in my first lecture, I described this theory called Deligne cohomology, which was a theory for complex manifolds. And then it's defined as the cohomology of a complex of sheaves. ZP Deligne, so for all P and Z, there's a different complex, which is defined to sit into a homotopy pullback square where you have a constant sheaf 2 pi I to the P times Z. You have the de Rham complex of the manifold, and then you have the Pth filtered piece of the de Rham complex. And then you take a homotopy pullback. So that was the main object in the last talk. But then at the end, I said what I was going to want to do in this series of lectures, and one of the main goals was to so fix the fact that while this Deligne cohomology is intended to be a refined recipient for things like Chern classes or Chern characters of vector bundles, it's actually quite far. So that if you take K0 of vector bundles on the manifold and you map this to sum of all the Deligne cohomology groups in the appropriate degree, this is very far from isomorphism. I sure can. Yeah, it help me as well, in fact. And the way we'll fix it is by replacing this K theory of a small category with K theory of a continuous K theory in the sense of Sasha of the big category. But to do this, well, we need to be able to define what this big category is. This is going to be some kind of version of a derived category of quasi-coherent sheaves on M. But if you're too naive about trying to define what that means, you run into trouble. So classically in complex geometry, there's a well-defined theory of coherent sheaves or vector bundles, which has good properties. But once you allow yourself to have infinite objects with infinite dimensional fibers, then things go wrong. So you have to be very careful when you set this up. And it actually took us quite a long time to come up with good definitions. But so what I want to do today is I don't think I'll get exactly to defining what this category is. That'll have to be the lecture after this one. But I want to set the stage by just talking about a different way of setting up the whole theory of complex manifolds, a way which will make it much more manageable to eventually define and discuss this category here. Okay? So, and this is all, I mean, basically everything I'm going to say from now on is joint with Peter Schulze. So the idea is so make it more like it being complex theory of complex manifolds. We'll make it a little bit more like scheme theory. So we're going to start with a class of rings. And then so if R is one of those rings R, then we'll let the ring, the commutative ring R, we'll let it determine everything. So there should be an underlying topological space. There should be a structure sheaf of holomorphic functions. There should be a de Rham complex. And there should be these theories of quasi-coherent sheaves, but again, I'm not quite gonna, yeah. Now for this, the naive choice when you look at classical complex geometry is to think, okay, well, the standard analogy, what corresponds to affine schemes over the complex numbers is objects called Stein spaces in the theory of complex manifolds. So for example, if you start with an affine algebraic variety, a smooth affine algebraic variety over the complex numbers, and you take complex points, you get a prototypical example of a Stein manifold. But from some perspectives, that's not going to be, well, that's not actually going to be, so the class of rings you might think you should take to be, well, an example should be maybe holomorphic functions on a Stein manifold. But that's not actually what we're going to do. We're going to do something different. We're going to take rings which will have some compact underlying topological space instead. And that'll make the topology match the algebra much more closely. Just like how in algebraic geometry, the spectrum of a ring is always quasi-compact, so here it should be the case that for the very basic objects we consider, the underlying topological space will be compact. So the basic example of an R that we'll be running with will be, I'll just write O whole D bar. So this stands for the unit disk in the complex plane. And this stands for functions which are holomorphic in some neighborhood of this closed unit disk. Yeah, so this is the closed unit disk, I'm sorry, compact. And we ask that for functions that extend to some holomorphic function in some unspecified open neighborhood of that closed unit disk. Well, you can also just understand these in a certain power series. So it's just some Cn t to the n such that yeah, there exists some radius, some r bigger than 1 such that some absolute value Cn r to the n is less than infinity. So just have some radius of convergence which is strictly bigger than 1. So that's what we're going to do. We're going to kind of talk about complex manifolds from the perspective of their compact subsets as being affine, or certain compact subsets of them as being affine, and the rings of functions on them. Which actually fits very well with what Sasha was explaining about K-sheaves on locally compact Hausdorff spaces, where sometimes it's convenient to look at sections over compact subsets instead of sections over open subsets. So what we need to do is we need to understand how such a ring can determine everything you might want to know. So let me start with the good news, which maybe is surprising. So the abstract, well, this is certainly a commutative ring under pointwise multiplication. It's also obviously a C algebra. It's an algebra over the complex numbers. And just that structure, the abstract algebra over the complex numbers, determines D. So more precisely, so we have D, and we can just look at algebra homomorphisms from this to the complex numbers. Again, just in the sense of abstract homomorphisms, and I claim that you can write down mutual inverse bijections. And this map is not so difficult to understand. If you have a Z in D, then you can send it to the homomorphism which evaluates your holomorphic function at the point Z. Okay. And this direction is also not hard to write down, because if you have a homomorphism, then in particular you can evaluate it on T, the coordinate, I mean the standard coordinate on the complex plane. And well, you'll certainly get something that lands in C, and I'll prove to you in a second that it actually has to land in D. Okay, so let me. So the claim is that these are mutually inverse bijections. And by the way, the same story works for polydisks in higher dimension. I'm just sticking to the basic case of dimension 1. So you can do D to the n, the unit polydisk in C to the n for any n. Just kind of working the simplest case here. So yeah, let me give a proof so you can see why this kind of thing holds. So, well, what are the basic things you need to understand? So need to know, you basically need to know that phi of t is always going to land inside D. And the second thing you need to know is that any phi is determined by this value phi of t. So this ring is the ring of all power series like this. In particular, you have the one where C0 equals 0, C1 equals 1, and Ci equals 0. Okay, yeah, yeah. Um, okay. Right. So okay. So the reason for this is actually remarkably simple. So if suppose you have a lambda in C which is not in D, then the function, so 1 over t minus lambda actually it lives in this ring. So or in other words, t minus lambda is a unit. And therefore so is phi of t minus lambda, which is the same thing as phi of t minus phi of lambda, which means that this is non-zero. So phi of t can't be equal to something outside the unit disk. Okay. So this is also simple. So the claim for this is that you have that the limit as capital N goes to infinity of phi of some n less than or equal to n Cn t to the n is always going to be equal to phi of sum over all n Cn t to the n. So if you're a homomorphism and you know the value on t, then you know the value on any polynomial. And then if you know this claim, you'll also know the value on anything and you'll be done. And the reason this is true is that the same argument as above basically shows that the difference same as above implies that the phi of the remainder, so some n bigger than capital N Cn t to the n, has to lie in the epsilon. So when n is big enough so that for n such that some Cn, yes, just some n bigger than n, absolute value of Cn is less than epsilon. Okay. Question? Can you speak up, please? No, it is the theory of complex manifolds. Yeah. Okay, so that's the good news. We get the underlying topological space. The bad news is basically, I mean, you can't get the structure sheaf or de Rham cohomology. Oh, I forgot to say, thank you. Yes, yes, yes. Of course, I only explained it as a set. Yes, I meant to make the point that there's a natural topology on. Yes, thank you very much. I think I skipped something in my notes. Yeah, thank you. Well, the bad news, well, it's okay. Never mind. Here's more good news. So let's say R is an abstract C algebra. I'm going to make a definition, so I'll define a topological space. As a set, I'm going to call it MBR. And as a set, it's just the homomorphisms of C algebras from R to C. As a topological space, I'm going to give it the subspace topology. So I take the product over all phi in R. Wait, no, F in R. Phi was my homomorphisms. F in R of products of the complex numbers. By definition, a homomorphism is a special case of a set theoretic map. And the set of set theoretic maps is this Cartesian product that has a product topology, and I give this the subspace topology. Okay? And then I claim that both maps are continuous. So claim both maps above are continuous. And the proof is obvious. To quote Sasha. but but it's really obvious. You just have to think. I promise there's nothing to it. Um, okay. And so the corollary is then that the topological space D as a topological space is determined as MB of this ring of holomorphic functions on D. So let me make a remark. What's the reason for the notation? The B stands for Betty. So it's a standard in at least in algebraic geometry to call the topological space of complex points, to call that the Betty space, and the cohomology on that usual topological cohomology, call that Betty cohomology. But it also stands for Berkovich, because it's equivalent to look at instead of the set of C algebra homomorphisms from R to C, you can also look at this set of multiplicative semi-norms on R. And this is actually the most convenient perspective for proving some of the things I'll be proving later. And if you do it that way, you can also do the non-Archimedean, do something in the non-Archimedean case as well. But I'm just going to keep it with this simple-minded perspective here. Okay. So that was more good news, but then there's the bad news, which is that you can't get the structure sheaf and de Rham cohomology, et cetera, just from the abstract C algebra, holomorphic functions on D. Okay. And, I could give you some reasons. The most basic reason, it might not be obvious why this is a reason, but trust me, it is. Is that if you take two copies of this ring of holomorphic functions and you tensor them together, it's not the same thing as holomorphic with abstract tensor product. It's not the same thing as holomorphic functions on the two-dimensional polydisk. And in fact, it's something that is essentially impossible to understand as a reasonable algebra. They have the same homomorphisms to C, that's correct. Yep. That's interesting. Yeah. Okay. So the solution to this is remember the topology. It's an infinite dimensional vector space over the complex numbers. Conventional wisdom suggests we should always be treating it as a topological vector space for the purposes of doing linear algebra. On holomorphic functions, and use a completed tensor product over the complex numbers. But we want to do it in such a way that we can continue the story tomorrow, i.e. that we can define this nice rigid category of nuclear so-and-so. So we should be very careful about exactly which formalism we plug into of topological vector spaces and completed tensor products. We want a very categorically friendly theory. So we want to, or rather, a category friendly version thereof. So what we're going to do is, instead of talking about topological vector spaces, we'll replace with light condensed C vector spaces. And instead of completed tensor product, we're going to use something called then the completeness condition is what's called gaseous. It's kind of the minimal choice. And then the completed tensor product is the gaseous tensor product. So before we had liquid, and then we did some things with liquid, but it turns out for the purposes of the nuclear story, it's actually better to use this gaseous instead. So for various technical reasons. Yeah. So one way you can do it is you can prove in the abstract Kähler differentials of this ring that like this is not true. Uh, yeah. Yeah. By suitably mapping to some crazy field, and using a transcendence degree argument, and then if this like so this okay. All right. So okay, let me continue the story. Talk about this light condensed stuff. So definition. So a light condensed abelian group is a presheaf on the category of light profinite sets. And this is the countable inverse limits of finite sets. Considered as a pro-category of finite sets, or considered as a full subcategory of topological spaces passing to the topological inverse limit. It's equivalent, it doesn't matter. It's a presheaf of abelian groups, yeah. On that, satisfying descent, the sheaf condition with respect to the first thing would be finite disjoint unions of these guys, and the second thing would be surjections of these guys, surjective maps between light profinite sets. So all surjections should count as covers. Now the So this category of light condensed abelian groups is a version of the category of topological abelian groups. And the idea is that instead of directly encoding a topology on a set, you will instead encode what are the continuous maps, what is, so to speak, the set of continuous maps from any of these test objects. And that organizes into a sheaf, and you just remember that sheaf instead of thinking about the actual topology. And then so yeah. So then you could take C. Well, we can take the sheaf, the light condensed set, or the light. Well, it's actually a light condensed ring. It's a commutative algebra object which sends a S to the continuous functions on S with values in C. Or, I mean, more generally, any topological abelian group. You can get such a thing. And then we can consider that's a ring object in this category. There's a tensor product, as with any sheaf category, sheaves of abelian groups. There's a tensor product. This is an algebra object, so we can consider C modules in condensed abelian groups, light condensed abelian groups. And that's our version of topological C vector spaces. But if you, and this has a tensor product, so this has a tensor product, but it turns out that if you calculate this tensor product, well, first of all, so every one of these guys has an underlying abelian group, which is when you take the singleton here, the maps from a point is the, so to speak, is the underlying abelian group. And it turns out that if you look at the underlying abelian group of the tensor product here, you just get the abstract tensor product. So when you take the tensor product in this world, you're not actually changing the vector space, you're just equipping it with some, you're not changing the abstract tensor product, you're just equipping it with some condensed structure. So it's not completed yet. So we need to pass to a full subcategory of complete objects. And again, we're going to use the kind of minimal choice of completeness. So, and the idea for this will be completeness will be defined to be essentially the following property. If you have so completeness of a C module M will mean that if you have a null sequence, then you get to sum some things. You can form the geometric series multiplied by the null sequence. So say 1/2 to the n, and you'll still get an element in M. So that's the kind of completeness that we're going to require. It's a very, very weak completeness because we're taking a null sequence and then we're multiplying it by this exponentially decaying thing, and we're only asking that that needs to converge. That's correct. The question, I'll make the remark later. It's a sequence that tends to 0. So so I'll explain it more precisely. So more precisely, so the most important light condensed set, the most important light profinite set is this n union infinity. So the 1-point compactification of the natural numbers viewed as a discrete topological space. If it's not obvious to you how to write it as an inverse limit of finite sets, take it as an exercise. And what is the interpretation of this? Well, giving a map from this, a continuous map from this to a topological space is the same thing as giving a sequence in that topological space plus a limit for that sequence, right? In the world of condensed abelian groups, so in Cond AB, you have the free condensed abelian group on this space, which would be the where homomorphisms of condensed abelian groups, light condensed abelian groups out of that, are going to be the same things as sequences in the target plus a limit for that sequence. But if we want to talk about null sequences, we should enforce that that limit point is actually equal to 0. So, and we can do that because we can just take a copy of Z, the free module on the set consisting of a single element infinity, which maps in there. And this, so this is the free module on a null sequence, or free condensed abelian group. I'm going to drop light on a null sequence. So the the data of a null sequence in the datum of a null sequence in a condensed abelian group is just the datum of a homomorphism from this particular object into that condensed abelian group. So the way to make this more precise is the following definition. So an M in mod C, where am I? Cond ab light is called gaseous. If you look at, now I'm going to look at the internal Hom from this null sequence space. And then I'm going to map it to itself by a certain map. And that map will be given by identity minus, and there's a shift operator times 1/2. And I want to require that this be an isomorphism. And this T is induced by the shift map. So n goes to n plus 1 from n to n, which extends to this thing here. So if you unravel what it would mean, that what this is talking about, this is some operation on null sequences. From given a null sequence, you take itself and subtract a shift of it multiplied by 1/2. If you unravel what it would mean to invert that operation, you'll find that you'll exactly need to sum geometric series like this. So this is a way of encoding that kind of completeness property. So oh, thank you. Remark, the condition is independent for 1/2 is equivalent to the condition for lambda for any lambda with absolute value of lambda less than 1. Thank you. What? Oh yeah, thank you. Thank you. Yeah. Right. Now, right. So the main theorem about this full subcategory of gaseous is that, so I'll call it so the full subcategory of M satisfying this condition, i.e. those M being, which are gaseous, I'll denote modules over C gaseous. And that's a full subcategory of just modules over C in condensed abelian groups, light. This is an abelian subcategory closed under all colimits and limits. And also all R lim, Ri lim, and all whatever higher derived functors of colimit, whatever. And also all internal HOMs, even derived for any I x. So for all x in mod C condensed ab. So it's got any kind of closure property you might imagine, except closure under tensor product. Yeah. Yeah, that's right. So and I'm gonna, yeah, so what? The question was, yeah, so I'll talk about the, you know what, so I'm gonna basically, well, if a question is such that I'm going to address it anyway in the natural course of the lecture, then I won't repeat it and instead just address it when the time comes. Yeah. Right. So I want to say something about the proof because so in previous iterations of this kind of thing, we had solid and we had liquid and so on, but and we would specify what those meant by essentially specifying what the free objects were. And then it was very difficult to prove theorems like this. Very, very hard work that we managed to do for these solid and liquid cases. Now it's different. We've defined gaseous by just a certain condition, not by specifying what the free modules are, the free gaseous modules are. And now it's really easy to prove this theorem. So everything follows from the interesting fact, which is one of the reasons for switching to light profinite sets from arbitrary profinite sets, that this object Z n union infinity, or the version where you kill the summand, is projective. So it's a projective object in the abelian category of light condensed abelian groups. In fact, it's even internally projective. So it's in the sense of internal HOM, you also have that if you have internal HOM into a surjection, then you get a surjection. Or internal HOM into an epimorphism, then you get an epimorphism. Once you know that, this is really, really easy to prove that theorem because there are no higher derived functors for the operations that are appearing here. And it's and this also answers the question asked by Maxime. If you want to do the derived analog, you just stick RHOM, and it's completely elementary that something will be derived gaseous if and only if each homology group is gaseous. So the derived theory is incredibly simple. And again, that was a theorem that we had to prove by complicated arguments with previous iterations of this theory, but now it's That's correct. But I also said we have it. Yeah, no, yeah. Okay. Um, R linear. Yeah, that's correct. Yeah. You would indeed. Yeah. So if you just impose that, what you need is you need your scalar that's a unit and is topologically nilpotent, and then see you could actually produce the complex numbers. If you could then you could make this definition in that context, and then you could prove that you get the complex numbers out of this when you set formally lambda equal to 1/2. So you can formally adjoin a variable which is topologically nilpotent in the unit, and then make this definition with that variable, and then you could prove that when you mod out by lambda equals 1/2, then you get the and you look at the unit object, you get the complex numbers, or the real numbers, sorry. But I mean, then you could, yeah. Right. Yeah, so this also gives a new construction of the real numbers. Thank you. Yeah. It's true. Well, maybe it's the usual binary expansion when you think about it, but okay. I mean, you don't have to explicitly talk about Cauchy sequences and null sequences. Anyway, or I guess you are explicitly talking about null. Maybe it's not so new. Okay, I'm gonna move on. Okay. Right. So I already said, yeah, so what's the upshot of this? So the upshot, um, so well, that's a nice category, abelian and so on. It's got basically all the good properties of a sheaf of abelian groups category. So there's a left adjoint to the inclusion called the gaseousification. I don't know. So from mod C con to ab light to mod C gas, there exists a symmetric monoidal structure on mod C gas, making this functor symmetric monoidal. So if you want to do the gaseous tensor product, you first do the condensed tensor product, and then you make it gaseous via this left adjoint. And then again, there's the derived analog of everything. And the derived analog is the derived category of that abelian category. Evaporation. Well, I don't know, because condensed is even less complete than, like, even less of a completeness condition than gaseous. So maybe, I don't know what it is. I'm not a chemist. Although I did teach chemistry students here in Copenhagen. Right. Oh, so let me give something. This is physics? Okay. All right. We're doing condensed matter physics, maybe. I don't know. Um, I started at 3. I realized that I'm not getting anywhere close to where I thought I would, but well, it's about the journey, isn't it? That's kind of sad, though. Um, right. So some examples. So any Banach space over C is gaseous. And what I mean is that given a Banach space, you can get a light condensed C vector space by, again, just looking at continuous maps from light perifinite sets in, and that thing is gaseous. That's, I mean, it's completely obvious from the definition. And then I already said it's closed under limits and colimits, so you don't have to ask me about Fauché spaces. They're gaseous too. You don't have to ask me about inductive limits of Fauché spaces. Those are also gaseous. So basically anything you encounter in traditional functional analysis which is complete in whatever sense, is going to be satisfy this very mild completeness condition. So for example, so in particular, this O whole D, which is naturally a filtered colimit of Banach space, a filtered union of Banach spaces, is gaseous. This is a filtered union, for example, of L1 spaces. Although there's a lot of freedom of what kind of filtered union you want to write down, but when I wrote the definition in terms of sequences, I said there exists an R greater than 1 such that something is summable, right? So that means it's a union of spaces of summable sequences with respect to some sort of transition maps, and those are naturally Banach spaces, and then you can, yeah. Okay, but speaking of this guy, which is of course our most important guy, so here's a theorem. This holomorphic functions on D is flat with respect to the gaseous tensor product over C gas. And you can actually calculate what tensoring with it does. And holomorphic D tensor any gaseous guy. It can always just be written also as a filtered colimit of spaces of null sequences, a sequential colimit of spaces of null sequences. So now I'm going to call this a null M. And it's you basically exactly write down the definition of this guy and replace the complex numbers by M, and you'll understand how to produce this sequential colimit here. So it's a very easy to do tensor product calculations in this category once you know this fact. And the proof uses trace class map tricks, which probably go back to Grothendieck's theory of nuclear spaces. But so there's actually a very general categorical fact which implies this computation here, and this computation implies this flatness. But I'm not gonna maybe give the details of that. Yeah, so that's an exercise for you to determine. And the hint is that when M is C, you should be recovering the definition of this guy. Yes. No, it's just, what's that? Well, I mean, they're basically you just basically, it's a diagonal multiplication by an exponential decaying sequence is kind of where, I mean, yeah, that's what I said here. Okay, other questions? No. It's quite hairy to try to describe tensor product of Banach spaces. So really you use the fact that the transition maps are trace class here to get control over this thing. Okay. Right. Okay, we're doing good. Let's see. So that's a setup for doing functional analysis, really, with a nice completed tensor product. Yes? I hardly know what the word monadic means, and I'm certainly not equipped to answer such a question. Yeah. Okay, thanks. Yeah, because it's a localization of a category of modules. Yeah, I guess I do know. Okay, never mind. Okay, well, anyway, okay. Okay. So what? So now I was saying, okay. Remember at the start, I said we're going to do complex geometry in a different way, and I said we're going to start with a class of rings, and then I said, oh yeah, the abstract ring knows the underlying topological space, but we need more. So we're not just going to start with some class of abstract C algebras. So we're going to start with our rings are going to be rings, so they're commutative algebra objects in the connective derived category of gaseous C vector spaces. It's going to be very important for us to allow derived phenomena here for the theory. It turns out then you go and calculate in case of usual complex analysis and you find everything lives in degree 0, but for setting up the theory, it's extremely important to pass to the derived world, and I'll explain why. Right. Excellent question. The question was, do I want connective E infinity rings or do I want animated rings? And the answer is they're the same thing because I'm in characteristic 0. And this is going to simplify my life greatly. Okay. So here's a definition. Oh, so F in R. So, okay, as I said, so really I should put a pi 0 here because it could be derived, but so it has an underlying ring, which is R of a point in this condensed framework. And then there's but that's not really a ring because it's derived. But then the pi 0 really is just a ring. Okay, the pi 0 of the underlying thing is just a usual C algebra. Anyway, so such an object is called topologically nilpotent if the homomorphism, and that's a homomorphism, I mean a map in this category. So we can make C, the polynomial ring is just a countable direct sum of copies of C as usual, to R, which sends T to F, factors through the map from this to this free null space. So I have to, there exists. And here I have to note that this is actually a ring. So this is a ring. And in fact, an algebra over the polynomial ring. So the free module on a null sequence is actually a ring in a natural way. Just like here, you can think of the ring structure as being induced by addition on the natural numbers. And you have to just be a bit careful about why it works, but yeah. Maybe not, but it'll turn out with all the different once I get to this is a helper definition, and once I pass to the definition I really care about, that distinction will be irrelevant for certain reasons. The question was whether it's equivalent to factoring as a map of without the ring structure. The answer was probably not, but it doesn't matter in the end. So you can imagine whichever you like. Okay, and then well, no, it's a condition. The condition is that there exists this extra structure. Yeah. Okay. Yeah, I hope I was clear with what I just said. Yeah. No, that was just asked, was whether yeah, so this in principle is extra structure on F, the datum of this map. But I'm asking the condition that such extra structure exists. Just like earlier today when Thomas was talking about trace class maps. But again, such subtleties are going to disappear when I pass to the next definition, which is the more important one. So that's topologically nil. Yeah. So and then I'll say that R is, let's say, pointwise bounded. If for all F in R, by which I really mean the same thing as there. For all F in R, there exists a lambda in C such that lambda F is topologically nilpotent. So if you can always multiply by a scalar so that you get something topologically nilpotent, meaning the powers tend to 0, basically, that's what this is really saying, right? Then you're called pointwise bounded. And it's pointwise because we're only talking about specific points in R or elements in the underlying thing and not S-valued families of points like plugging in a general light condensed set there. Thank you, yes, yeah. And maybe I'll just restrict to the same lambda as before. Thanks a lot, Akil. Yeah. Right. Yeah, I did say that orally, that I really mean secretly the same thing as over there. Yeah. Okay. So um yes, it's not a localization. No. So now this is basically the condition we're gonna be putting on our rings that we'll be considering, and then we'll produce the whole geometry from that. It's basically just this pointwise boundedness condition. This will make we'll be able to define this underlying topological space, we'll produce a structure sheaf, we'll prove all sorts of things just using this condition. However, it is actually more convenient to require a strengthening of this, which talks about not just pointwise bounded, again, this is the point I'm referring to, but makes a condition for arbitrary light profinite sets sitting here instead. And the possibility of making such a stronger definition was well, the person who it's due to is Juan Esteban Rodriguez Camargo. And so I will give the definition which he describes, or maybe a form of it. So definition. So how to extend this definition to S-valued points. So an F now, which is an S-valued point in R, so S a light profinite set, is, let's say, uniformly topologically nilpotent if we just kind of do the same thing. So you can get a map from the free algebra on S, which is kind of disjoint union over D of sim ds mapping to R. So this encodes F, and this should factor through a null sequence, sorry, a null. So disjoint union sim ds, union infinity mod infinity. So so it's saying that if you so you have an S-valued family of points in your ring, and you want to know that when you take d many products of any of those S ones, not necessarily equal to each other, but when you take d many products and have d go to infinity, all of that will go to zero. So it's different from just requiring it pointwise, that if you take any point in S and look at the corresponding element of the ring, that's topologically nilpotent. Because you're not just looking at F to the n, you're looking at like products like F1, F2, F3, F4, and asking that when you have enough things multiplied together, that it's always going to tend to zero. Yes? No. So, right. And then, right, so R is bounded if for all S and for all F in RS, there exists a lambda 0 less than lambda less than 1, such that lambda F is uniformly topologically nilpotent. Now, so an example, by the way, maybe I'll state the reason we like this property versus that property. It won't be ever used explicitly in what I'm going to discuss, but the reason for preferring bounded to pointwise bounded is because bounded, the category of the bounded property has excellent closure properties, which are very difficult to check for pointwise boundedness. This gives a candidates for giving counterexamples. So the C alg d greater than or equal to 0, C gas bounded, so the ring satisfying this condition is closed under all colimits and finite limits. So this is, again, Rodriguez Camargo. And recall that filtered colimits are always just calculated on the underlying level, but finite colimits involve relative tensor products. So we're claiming here that relative tensor products of bounded rings stay bounded. And the tensor product is this gaseous tensor product. Okay. And an example of a gaseous, a bounded gaseous. So if R is any Banach algebra over C, then R is bounded. And now you learn also that any filtered colimit of Banach algebras, or any tensor products of Banach algebras, and whatever you might do to whatever you have, then you're still going to stay in the realm of these bounded guys. And also in particular, so this O of D is bounded. And if you have R bounded, then R tensor with this is bounded, and so on and so forth. So it's very, very convenient to be in this bounded framework. Now, I think I started a bit late. Is it okay if I take two minutes? Thanks. So I just want to state the main theorem. Well, but a vague form of the main theorem, and I'll give the precise form and the consequences next time. So theorem, if R is pointwise bounded, then remember this guy? Hey, remember me? I was a topological space. I talked about way at the beginning of the talk. Then this is compact Hausdorff. And I'm going to say that dr. I want to introduce this notation. So this is R modules in derived gaseous. This localizes along MB of this abstract, the underlying abstract C algebra. So there's something very funny going on here, that we're using the underlying abstract C algebra to make the topological space, but we need more. We need the condensed structure to produce the category of sheaves, of quasi-coherent sheaves, and the structure sheaf and so on, and to do the linear algebra we want to do. But it all works, and I'll explain why next time. Not necessarily. Yeah, even for a bounded, it's not true. Now, in usual examples, like the examples relevant for complex geometry, it's true. But in this abstract framework, it's simply not true. So you really need to use the abstract homomorphisms. I'm sorry, the question was whether this, which was defined as the abstract homomorphisms of C algebras from R to C, whether it's the same as the condensed homomorphisms, from R to C, or continuous, whatever you like, continuous algebra homomorphisms from R to C. And the answer is no, they're not the same. Although the other part of the answer was they are the same in all the examples I'll be discussing. But yeah, okay, sorry, go ahead. Correct. This also, yeah, by construction, this only depends on pi 0 R. Yeah. Well, who knows what the future holds? You're not going to encounter them in this lecture series, I'll promise you that. Excuse me? How are you parsing it? Yes, before, do you remember when I defined MBR for R as C algebra? Exactly. So this is a C algebra. Yeah, exactly. And maybe I should put pi 0, but I mean, it doesn't really matter, but yeah. I'm sorry? Unital, yes. Yes, Richard. Yes, all my algebras for now are unital. Yeah. Well, I defined it earlier in the lecture. Yeah, it's the weakest, strongest. It's the topology such that the strongest, weakest. Course's topology is such. Thank you, Courses. Course's topology is such that all evaluation maps to complex number, like given a homomorphism, you can evaluate it at F for any F in the ring, and you want that, which is a map to C. You want that to be continuous with respect to the usual topology on C. Yes, Akil? Oh, you're speaking very softly, and I can't hear. In 10 minutes, that's plenty of time. We'll be out of. Yeah. Okay. Okay. Yeah. Why don't we save the questions for the beginning of next lecture? Okay.